Hello, I'm Hyoungsu Park, Assistant Professor in University of Hawaii. Here I present about experimental study of deep advection driven by tsunami-like wave. And here is a list of my co-authors of these presentations. So coastal disaster like a hurricane and tsunami generate and transport lots of debris to inland. Those debris could cause negative effect on resilience of coastal community. However, there are relatively limited research for deep advection, and it is hard to predict its quantity and its final dislocations. So in this study, we try to have better understanding of debris transport through experimental study. Especially, we evaluate the effect of different density of debris elements as a group. Also, we evaluate some effect of obstacle on the debris passage. This presentation composed of 5 sections. I just covered the introduction and other sections will go on. And then this photo actually show our test bed and some of our debris we used and some obstacles we used for our test. This photo give a detail our test bed, and that is performed in the 3D wave basin in Oregon State University. And actually this unique setup had developed for collaborate research project from last PI in USA, and some of researchers actually join in. And there are lots of research using this experiment setup, and here is my research. This figure shows the sketch of our experimental setup. Our test bed has the 10 by 10 meter flat regions, and we located our debris here and run the wave. And it connected to some slope, that is slope on over 20 slope. We also install lots of wave gauges and ADVs to measure the space hydrodynamics, and we also install 4 cameras on the flat regions to measure the debris motions. Here are another photo of our test bed, and you can see some gridded line. That is a 2 meter by 2 meter gridded line here, and this is the movable bridges. So we install some ADB and ultrasonic wave gauge here, so we can change the location of these bridges to measure the various surface elevation and velocity. And here are some detailed photo of wave gauges and ADBs. Information of debris elements. We prepared 2 identical square box-shaped debris, but use 2 different materials, HDPE and wood. And here is the density of HDPE and wood. That is less than the water, but HDPE is mostly close to the water, and while the wood is about more than half of water. We choose this square shape to avoid the orientation issue and during the transportations, and the length scale is about 10 centimeter to the length and width, and thickness about 5 centimeter. And also we adding the HDP layer on the wood debris to give a same bottom roughness. So actually HDPE and wood actually show the same friction conditions. And we keep the same size too, right? And here are some information of grouping. So 20 of debris elements composed of a single group, and those groups actually indicate as the specific gravity of that group. So in case of wood debris only, specific gravity is 0.65, and in case of HDP only group, specific gravity will be 0.99. And there are other 3 groups has a different number of wood and HDPE, and actually because of that, they show different specific gravity, 0.74, 0.82, 0.91. Here are some information of initial configuration. We set up the initial position of debris uniformly or checker or randomly, and we test many of cases, changing those information and also changing the specific gravity. And this table actually show that the 1 to 10 case show the without obstacle on the passage, and 11 to 18 case show the case with the obstacle. And here's some example video clip without obstacle. Actually, we combine the rectified 4 images from the camera and making as a one merged one. Okay. And this kind of the video clip and their location of debris digitized from the MATLAB. And we measure the 3 things: spreading angles, how much they deviate from the orientation, and the longitudinal distance, their movement to the x directions. And also we measure the average velocity at the 6 sections, section 1, 2, 3, 4, 5, 6. And each section have a 100 centimeter unit distance. Okay, here are some results. So this image actually shows the final dislocation of all debris trial without obstacles. And this black and blue dashed line indicate the spread angle prediction from the previous research. If we take a look at detail for each specific gravity conditions, the left side shows the change of spread angle for the HDP debris, and right figure shows the wood debris only. So here each square box indicate the spread angle of each debris, and then this thick line indicate the average spread angle, and the blue rectangle indicate the confidence intervals. As increase of specific gravity, HD debris spread angles are increasing, right? But wood debris actually show the quite uniform result. And this slide shows the change of the longitudinal distance as change of specific gravity in the group. As increase of specific gravity, the distance of wood debris is linearly decreased. However, the HDPE showed quite uniform result. And also you can observe the specific significant deviation for the wood debris, you can see here, but the relatively small deviation for the HDPE. So now we can show some result with obstacle. And this is some video clip with obstacle. So you can see that there's an obstacle to obstacle, and the distance from the shoreline to the obstacle is about 4 meters. And this cube-shaped obstacle has 46 centimeter length and width and height. So here are some final location of all debris trial with obstacle. We plot them for the different number of obstacle case, 2 or 4 or 8 obstacle, and you can see that after 4 obstacles, there are relatively less change of those patterns, and we can observe that relatively the distance are decreasing and their spread angle also decreasing due to the obstacle. So at this point, we focus on some collision ratio to the obstacle. So we count the number of debris which fully or partially collide to the obstacle. So we found here that in case of lower specific gravity, like a yellow one, so wood case, actually show the 58% of collision ratio, but HDPE, which has the heavier specific gravity, actually showed 25%. And if the specific gravity is the kind of middle one, that showed actually middle 37%. If we take a look at detail for this, we can observe that some of HDPE collision ratio actually increased, but the wood debris actually decreased because of they are mixing together. So we can observe some minor impact of the debris interactions due to the different density, right? And they result in some difference on the collision ratio too. We also measure the velocity field. We measure the velocity of each debris at the section 1, 2, 3, 4, 5, 6. And we measure the leading edge flow velocity with and without obstacle, and also measure the HDPE and wood debris with and without obstacle. And here is some result. So here, the blue line indicates the leading edge flow velocity, and then black is for wood debris, and red is for HDPE. So we can observe clearly difference on the velocity for each debris and leading edge flow velocity. And also, though, we can observe the relatively leading edge velocity showed quite uniform, right? Oh, by the way, here the dashed line, each case indicate the velocity with the obstacle. So you can observe some changing of some decrease of velocity due to the obstacle case when they feel the obstacle, during the advection. So in here, you can see the debris case. They are relatively small velocity at the section 1 due to the debris entrainment process. After that, they reach some maximum velocity and they are quite uniform up to section 4, and they are decreasing again because they feel the bottoms because of the relatively shallow elevation in this location. Okay, conclusions. So we can clearly observe the effect of different density in the group, and it changes some longitudinal distance, spreading angle, and collision ratio, and advection speed. And those kind of information are summarized in these tables, so you can maybe check that carefully about that if you want detail. Kind of conclusion is that we observe generated from the conclusion. Kind of this conclusion we observe here actually generated from the complex interaction among debris and flow, and debris and debris, and debris and obstacle. Therefore, it is necessary to consider kind of group debris density condition for better prediction model for debris in future work. Finally, there are some limitations. We didn't concern about the many variation or debris setup, like shape, size, or number, and we don't concern about slope conditions and no return flow in our test. And our scale is 1/40, so maybe not a little bit small. So that